So we're looking at torsion now, which is a twist about the center of a shaft. And we're on page about 580. We started this just a bit. We'll kind of finish up the derivations and then look at a few examples, like we do. All right, so torsion is a twist generally about the center of a shaft. That's how you think about it. It's a type of moment. Okay. Now, there's few kind of ideas that we want to link together here in strength materials. The model I think of for torsion is like a stack of pennies or something that have elastic glue between them. So, and if you think about applying this torsion here that I'm showing at the end right there, that's going to twist each penny just a little bit with respect to the previous one. So if you start with a horizontal line down the stack of pennies and you twist it, that line will rotate a little bit. Okay, on the pennies themselves, you can look at a little area. There'll be shear stresses that build up as one penny tries to slide across the other. If you sum up the stress times the area is a force. Okay, and if you multiply that by the offset distance from the center of the penny there, which you could call rho, that'll be the torsion, the moment about the center of that penny there. So that'd be, the force would be tau dA, and the offset distance would be rho. If you add that up for every possible area in the penny, what you end up with is the torsion about the shaft. That's one of the fundamental relationships there. So one of the big kind of ideas here, connections, is the connection between torsion and shear. Because torsion is trying to cause a shearing action. That's what it's trying to do. Right? We could then look at these relationships here. If we take the outer layer of the shaft and kind of lay it on the table, we could also take a layer from E to E prime there on the inside and lay that on the table. You get these kind of fundamental relationships here. So what we have here is an arc distance right there. What we would have then is that arc distance would be r, the radius, times whatever that twist angle is on the shaft, because when you apply this torsion, you're going to twist this line a certain angle. We call it phi. That's the twist angle. So if the twist angle is in radians, either r for the outer radius or rho for a radius to some point in the middle that I'm calling e times phi will get you that distance. Okay. And then if you look at how this little square element here would change shape as it rotates up, it would do something like that. You get shear strain on that. This angle here is equal to that. Same thing on the other side there. So what we notice here is a couple of things. The first thing is that distance increases, that arc distance increases as you get further and further out of the shaft. So that arc distance from B to B prime is larger than the arc distance from E to E prime. Okay, they're different distances. The further out from the shaft you go, the bigger they become. Also notice for that same twist angle, because those distances are r phi and rho phi, it's the same phi, you get more shear strain as you work your way out from the center of the shaft. So this strain and also the stress is maximized on the outer layer of the shaft. Okay. You also have a constant ratio between that strain and how far from the shaft you are. So as you get further and further from the shaft, center of the shaft, I should say, center of the shaft, the shear stress goes up in a linear sort of way. All right. And that gets us to these derivations here. The key idea is that the shear strain divided by the distance from the center of the shaft is a constant. You can multiply by G and get the shear stress. So the stress is maximum the further you get from the center of the shaft, and it's a linear relationship. So the torsion then is the integral of rho, the distance, times tau dA, which is the force. We can then work with that mathematically and get the relationships. The first thing we'll do on this side is we'll put in just a factor of rho over rho, which is just 1. We can put that into that expression. But what that allows us to do is to rearrange things a little bit and get a tau over rho, which is a constant. So that can come to the outside of the integral, and that leaves rho squared dA on the inside of the integral. Well, what rho squared dA is the moment of inertia. It's a polar moment of inertia. Okay. So that expression then becomes the torsion is the shear stress times the moment of inertia divided by the rho there. If we can solve that for tau and maximize rho and maximize it into r, we get this equation right here, which is our maximum shear equation. Okay. So that's the maximum shear stress in a shaft. It's the torsion times the radius divided by I. So that's one of the equations that we use. So we got any questions on that one? Okay. Now that's one of the things you design for is shear stress. Now another thing you design for is the twist angle. Because if you have too much twist in a shaft, it may not align itself properly. It may not work in the way you want it to work. So we look at this twist angle also. So that comes from this shear strain is rho phi. Phi is the twist angle. Rho or r is the distance from the center of the shaft divided by L. Okay. We can solve it for phi. It's the shear strain times the length over the radius. We can then put in a term of G over G in, which again is just 1. The shear strain gamma times G is tau, so we can solve that for the twist angle, tau times L over RG. We can then substitute this expression in for tau, and what we end up with then is a relationship between the twist angle, phi, and these other factors that go into a shaft, the torsion, the length, the moment of inertia, and G. So phi is equal to TL over IG. So those are the two key things we look at when we analyze and design shafts. So we look at, when we do that for torsion, okay? So what we look at here is the shear stress, which is equation 91, and the twist angle, which is equation 93. Now these do make a certain amount of sense when you look at them. Okay, tau max, if you want to maximize the shear stress, okay, the bigger the torsion is, the bigger the shear stress, of course, the bigger the torsion that's applied to the shaft. The further out from the center of the shaft you are, the bigger the shear stress. So that's what R is, it's rho max. And then moment of inertia resists, it's the property of a shape and how well it resists these bending or twisting type actions. That's why that's in the bottom, because you have an inverse relationship for that. Okay. Similarly, for the twist angle, you have these things that kind of make intuitive sense. The bigger the torsion, the more the shaft will wrap up. The longer the shaft, the more extreme that twist angle will become. So here we have a shaft that's had a torsion applied, like that. So what happens is if we start with a vertical line and we look at how that twists, there's the twist right there, that's this distance. Well, if you have a longer shaft, if you have a longer length out to there, that'll twist further. That point will twist further as you work your way out from the origin of the shaft, okay? So the longer the shaft, the more it wraps up, the more it twists. So L is on the top of that relationship then. The moment of inertia resists twisting. G is how stiff the shaft is in shear. It's the shear modulus. So the moment of inertia and G are on the bottom of the equation. So those are the two relationships we use, okay? I've also got, so we got any questions on that stuff? Doing all right? Okay. On 586, I've got a little bit about moment of inertia and how you calculate it. If you remember this from statics, moment of inertia is the integral of a distance squared times an area. Now for shafts, because they're usually round, that's done in a polar sense. So if you look at these round shafts, what you do is you break them up into a series of, I think they're called shells in calculus. The area of a shell then would be its circumference, because what we're going to do is take that shell and just kind of cut it and lay it out flat. So we'll cut it right there and lay it out flat. Its area then will be 2 pi times the radius of it, which we're going to call rho. Okay. And then you would multiply that by the thickness, and that would be d rho. Okay, like so. Okay. So what we have there is the area, the circumference, 2 pi r, or rho. Rho is a more general term for measuring out from the center of the shaft to a location you want to measure to, anywhere in the shaft. But then the thickness will be d rho, kind of working your way out. All right. So that's the area. So now we can run these integrals for a solid shaft. The moment of inertia, usually subscripted with a P for polar, because we're doing this in a polar sort of sense as we work our way out, would be these areas, which is 2 pi rho d rho, times the distance out from the center of the shaft to the areas, which is rho. You square that though, so that's rho squared dA. So there you go. And we just have to evaluate that integral then, okay, as we work our way from the center of the shaft out to the edge. So we got rho squared and another rho, that's rho cubed, and then a d rho, and then we pull the 2 pi out in front of the integral. There it is, okay. So now we got 2 pi times the integral of rho cubed d rho. Well, the integral of rho cubed d rho is rho to the 4 over 4. Plug in the limits, because we're starting at the center of the shaft, working our way out to the outer radius, so those are 0 and r. We get 2 pi r to the 4 over 4. 2 over 4 is just 1 over 2, so it's pi r 4 over 2. Okay. So that's the basic formula for the moment of inertia of a solid shaft. I've got that, that's equation 94. Now, if you've got a hollow shaft, which is often done because it's a little bit more efficient shape, what you do is you take the outer radius, so that'd be pi over 2 r 2 to the 4, and then you just subtract off the inner shaft that you've cut out to make it hollow, so that's minus r 1 to the 4 over 2. So there's the moment of inertia for a hollow shaft right there. And those are equations 94 and 5. So we're doing all right with that? Okay. All right. Let's look at a few examples here. 600. So we've got that shaft there. It's hollow. Why don't you just calculate that moment of inertia and just verify that it's 3.94 times 10 to the minus 6. So have a look at that. What we want to do here, normally, you know, when I have a shaft, I want moment of inertia, we're going to apply this torsion, and we want to find the two basic things. We want to find the twist angle and the shear stress in the shaft. Okay? Both of which involve the moment of inertia, so we just want to calculate that. So pi over 2, outer radius to the 4, inner radius, we'll subtract off the inner radius to the 4. And what you want to do there is, the one thing on this, well, two things, you know, just thinking back to things I've seen over the years. Remember the radius, not the diameter. You know, we spec out round things by their diameters, but what goes in is the radius. I keep it in meters. And then remember to take it to the 4th power. That's what the equation calls for. Just a little bit of a calculation there. Yeah, we want at least 3-figure accuracy. Sometimes I go 4, but 3. I'm not too worried about it. But and these metric ones for common shaft diameters usually come out to be sometimes 10 to the minus 6 is usually what I end up with. We're getting that all right? 3.94 times 10 to the minus 6. So it's
exactly 4 times 10 to the minus 6.
so 0.04 to the 4, then take away 0.015 to the 4. Okay. Doing all right?
Yeah.
All right. So this moment of inertia type stuff, there's things I calculate right from the beginning, one of which is I. I want to get that, and it's a polar I, so it's pi over 2, r2 to the 4 minus r1 to the 4. So we good with that? All right, then what we want to do is we want to figure out the shear and the twist angle. So the shear is just the torsion times the radius divided by I, and the twist angle is the torsion times the length divided by IG. So it's just a matter of plugging everything in and running the numbers. There's just some conventions on this. Just remember to use radii when that's called for. Also, the twist angle, if you do the dimensional analysis, the units come out to be null. They come out to be nothing, what that means is a radian. A radian is a unitless angular measurement. So if you want something that might be a little bit more intuitive, you convert that into degrees. I always have trouble kind of visualizing radians, what 0.02 radians is.
Is the torsion, is that a negative? Is that going to be a negative since going? Or not minus going counterclockwise?
Well, it's a good point though. Yeah, that is as shown, that's a positive torsion because right-hand rule kind of thing. So, as shown there, that's positive because if you roll your right fingers in that direction, your thumb will point to the right. So you're right, that is a positive torsion there by convention. Okay. I don't get quite as particular as this on signs with torsion as I might like with moments or something. There is a positive and negative sign to it. All right, so what we've got here is we've got a 1.19 degree twist in the end of the shaft. So, and now, you have to think about what you're doing with that, your shaft, and see if that's tolerable or not, whether you could live with that or not, that amount of twist. Got any questions on that? There we go. Okay. All right, that's it's just the most basic application of the equations. Now, we get into different situations. I mean, what we just said there is, okay, I know what's going to happen to that shaft. I know what it looks like. What will the shear stress be and how much will it twist? These are the things you'd look at. These are your design values then, or the things you'd look at. You look at your material and see if it could handle 2.13 megapascals of shear. If it can't, you're going to need to make some sort of modification, a stronger shaft or a bigger shaft or less torsion or something. Okay. And then you look at this twist angle. We'll look at that in a second to see what the repercussions of that are. Why don't you find somewhere to sketch that twist angle? Just take a minute. What is that, okay? Then let's kind of get beyond just a number and get into what that means. I mean, what is that twist angle? If I were to sketch it on there, what would it look like? Because this is something we want to know, of course. There's a couple angles that are happening here, and it is important that we keep them straight, okay? The angles are shown on, well, where are they first shown? They're shown a few different places. Let's kind of have a look. They're not really shown, well, they are shown on 580. They're probably better shown on 581 or 582. 582, anywhere, 581 or 2, or where they're shown. All right. I used to be able to explain this stuff using analogies like tuning up your car and stuff, but I don't think anybody tunes up their car anymore. They used to have something called a timing light, and you had things called points in a car. I mean, I'm talking about. What's that? Huh?
I was shocked the hell out of myself.
Yeah, right. Yeah, you've done it.
When I was so young.
Yeah, if you shocked yourself, you've probably done it. Yeah. But that had so what would happen there is you'd be looking, you kind of adjust your distributor cap and get advanced. Well, anyway, we don't need to go all that, but you used to time when the spark came to the cylinder on your car, and you used a strobe light, timing light. Yeah, and there's 2 tick marks that would match up, and that was a pretty good example of this idea of twist. So if I put a mark right here, and there was a mark on these things. What the twist angle would be if that mark was right there. What this is saying is this point would, and I'm really exaggerating it just so I could draw it in there, would twist over 1.19 degrees, okay? That's what that twist angle means. Now, if you have a rotating mechanism, a good example again would be an internal combustion engine, where you've got one crankshaft that's driving all these things, right? The crankshaft turns the pistons. It also turns the valves and all that. Now, if there's twist in that shaft and those valves aren't opening at exactly the right moment because that shaft's a little bit twisted, you got some problems there, right? That's going to throw your whole running of the engine off because the valves aren't closing and opening when they're supposed to, okay? So there's an example of why you might be concerned with this. You couldn't tolerate too much twist in a crankshaft unless you'd already designed for it, because it'll throw essentially your timing off. The engine's not running properly. So there's an example of why you might care about that number. Okay. All right. So we good with that? Okay. All right. This next one here. We good? So 602, this is the same sort of thing, but now instead of saying, okay, I know what the torsion is, what's going to happen to the shaft, now I'm saying, well, here's what I can tolerate, okay? I can tolerate 160 megapascals of shear, and the twist angle can't exceed 2.5 degrees. How much torsion can I apply? So it's the same equations, you just have to solve them for the torsion now, is what you would do with this. Now, whenever I see these torsion problems, I immediately calculate moment of inertia. Pi over 2R4 there, it's a solid shaft. But the other thing is, units are important in torsion. They come up a lot. So 2.5 degrees, that's a perfectly reasonable angle, but the formula uses an angle in radians. So I would convert that into radians. It'd be 0.0436 radians. Okay. So remember to make that conversion for any sort of angles. They should be in radians. If you ever need that conversion, it's on the formula sheet, lower right-hand corner. There's pi radians is half a circle, 180 degrees. Okay, so I start with that. And what I do next is I just use those 2 basic equations, one for angle, one for shear, and I rearrange them and solve them for torsion. And I just plug the stuff in and I'll get 2 torsion. Okay. So I got tau as TR over I. So the torsion then is tau I over R. And phi is TL over IG, so the torsion is phi IG over L. I just plug those things in. Now what's going to happen for that is I'm going to get 2 torsions out. One for the shear stress, allowable shear stress, and the other for the allowable angle of twist, that twist angle. So I'm just solving that backwards is what I'm doing. So, what's the maximum allowable torsion? Yeah, there you go. It's funny because people see that word and they always want to pick the bigger, well, not always, but people see that word. There's a danger when you see that word of picking the bigger. You don't want the bigger. When you design stuff, you want low load, biggest size. That's the things you design for, right? So if you're in charge of designing something, you want to minimize the load, pick the lowest allowable load. Or if you're designing for size, you pick the biggest size, okay? So yeah, you're going to go 26,600. That's as much torsion as you can apply to that shaft, because if you exceed that, you're going to have too much twist. Okay. So what we're doing here, we're going into this, we're saying, okay, for this shaft, I can only tolerate 2.5 degrees of twist for whatever reason, and I can only tolerate 160 megapascals of shear stress. So how much torsion can I apply? So we're just backing in to that allowable torsion. Got any questions on that? Okay. All right, so that's kind of the basics right there. There's those two equations, the two things you look at. You look at shear stress and you look at twist angle. So let's start doing some different situations you can run into. But first, let's do this here. So we we did do the deal here with the twist angle, having a look at that. How about this? How about if we've got a square tube? I don't have this in your book, so just put this somewhere. Let's just be sure that we all have this concept down. So let's say we've got a square tube, okay? Structural tubing is usually made square or round, okay? Usually made out of plate, okay? But let's say we've got this square tube and we're gonna hang a plate from it. And the plate weighs 600 pounds. How much torsion is being applied to that square tube? Real quick calculation, but I just want to be sure everyone kind of gets this idea here. So if I have that square tube, and again, this is not in your book, so you just have to sketch it up on the back of one of the sheets or something. And I've just attached that plate to it, and the plate weighs 600 pounds. What's the torsion about the center, which is normally where you take it, the center of that tube? What's the torsion? Because this is what torsion is. It's just not, a number in a book. It's caused by loading of some type. Or, the two most common sources of torsion I can think of is a weight at an offset, as we're doing here. Another would be some sort of true, like a couple, if you remember that from statics, that you're driving something. You've got a spinning pulley or something, and you've got a load on that. That would be the other source of it.
What's that last dimension that you have on, but the 600 next to 4 inches?
1 inch on 1 inch, 1 inch. Is that so? 4 inches, 4 inches, 1 inch, 1 inch. I'm sorry.
That's like down the middle of the plate.
Yeah, so I'm putting the load in the middle of the plate, and the plate is a 2-inch plate, and I put the load at the center, which would be in the middle, if that makes sense. Okay. Y'all get into something on that? Real simple calculation. There's not much to it. But it's the concept is what after, I guess.
It's just that moment right there.
Yeah. Moment about the center of the shaft. Yeah, so just a moment about the center of the shaft. Just a moment like what you learned about in statics or physics even. The one thing is you take it around the center of the shaft. That's the convention. what do we got there? What's that? Yeah, 300 inch pounds, yeah. Pound, let's see. 300 pound inch, I think, is normally the units, or inch pounds, I don't know. I don't really make too much difference. So yeah, we just find the moment. It's going to be the force, 600 pounds, times that offset distance, 5 inches. Because yeah, we're going 4 plus 1 more. Now, if you want to, by right-hand rule, see that's clockwise, you could put a negative on that if you wished. It may not be a huge deal to do that, but it might. So there you go. Okay, so 300 pound inches. We okay with that? Because
No, I screwed out.
what's that now?
1 more 0.
1 more
I
0.
screwed that up.
Yeah. Okay. Thanks. 3,000. Thank you. There we go. Yeah, we're in pound inches. All right. So that's what torsion is. So keep that in mind. That it's not just a curved arrow with a number on it in a book. That's what torsion is. Okay. And you can think about that. If you attach that plate, that shaft would start to twist a little bit. You can kind of see that. Okay. And you get shear stress building up in it. So that's one kind of starting point. What torsions are. But now let's look at how we analyze multiple torsions, because this is something that can come up. This is 609, is what this is.
Question about the last one.
Yeah.
Because that plate's hanging from the whole length of that square tube, so it's going to twist the whole tube equal proportions along its length.
Well, that's a good point. That's going to get a little tricky, because you're right. It's not just 3,000 pound inches applied at the end. This would be a distributive torsion. So you'd have to probably, if you want to get the angle on this, there'd be a few factors that would complicate that. But you would have to kind of integrate that, I think, and kind of work it as you go. That would be a little trickier than what we've been looking at so far, because it's not a point load. It's a load uniformly applied over the length. So that would be a little tricky. Okay. All right, so let's have a look at this one here. What we've got here, we've got 600, I'm on page 609. So we've got this motor shown, and this is a little bit, not quite the same, but it's on the same idea. We got 2 torsions applied here, 2 pulleys. So we've got a motor with a shaft going, the motor's at A, shaft to B has a 6 centimeter diameter, then from B to C it's got a 4 centimeter diameter. And let's figure out how much this shaft is twisting up as you work your way out from the motor to B and then from B to C. And let's also see how that twisting would affect the timing on this thing. And again, this is, and I don't know if they, this used to be such a common term because people used to work on their cars a lot more than they do now, but it was called top dead center. It's a line that's drawn vertically on something round that's going to rotate. It's 12 o'clock, okay? But once this thing starts spinning, that's not going to be 12 anymore, because you're going to have a load applied, and that's going to twist that shaft a little bit. And if we know the angular speed of the shaft, let's kind of get the difference of when both of those points, B and C, hit that top dead center, okay? All right, now let's look at something here for a second. What's our twist angle formula? It's TL over IG, right? Now, a twist is a fancy word for it is an angular displacement, if you want to get all fancy about it. Well, we've looked at a displacement formula before, haven't we? Linear displacement, which is delta. What's the formula for that? PL over AE. Do you see some analogies there? There's an L, there's an L. Okay, let's start with that. It's a good place to start. What else do we got going on here? Now, linear displacement is about axial force, right? There's the modulus of elasticity, which is an axial modulus. Look at that, there's the shear modulus. Okay. Now we got a load, a linear load, an axial load, but there's torsion. That's an angular type load, isn't it? Okay. You with me here? And then also we have the primary shape property that resists the load. Okay, kind of, I don't know, might have kind of a mouthful there, but what resists the load when you pull on it? How big it is, the area, right? But what resists the load when you start twisting it, the moment of inertia. See, those are analogous formulas. They're just for different situations. The one on the bottom is for stretching something out. The one on the top is for twisting something. But they have the same sort of things you put in, just a little bit different versions because they deal with different situations, okay? So if you remember doing these multiple deformation problems, it's the same thing here. We're going to do the exact same thing. I even like to set up a table as I had, kind of showed you to do for those PL over AE problems, okay? So for each section of the shaft there, I'm going to have a different torsion, different length, different moment of inertia, and possibly a different modulus, okay? Maybe not, I guess they both have the same modulus, but it's the same idea. And just as with those linear problems, you're gonna wanna start at the reference point, which will be where the motor is, point A, and then you're gonna wanna work your way out and find the internal torsions, the one that occurs from A to B, and then another one that occurs from B to C. So it's the same idea. Okay, so let's kind of work through that. I got the sum of torsions is 0, so I can find that torsion at A, okay? So what I've got then is the torsion at A is negative 200 Newton meters. Because you can see I've got the 120 and the 80 at the pulleys. What that means is essentially that reactive torsion at A is 200, but it's negative, meaning it rolls into the page. By the right-hand rule, that's negative, okay? So that's going that way. If you roll your right fingers that way, your thumb points in the negative Y direction as I have this drawn up. So that's why that's a negative, okay? So I'm summing up the torsion, setting it equal to 0. I'm finding the torsion at A. It's 200. Then what I'll do, I'll start working my way out from there. Okay? And just as we did with those linear shafts, it's the same idea. I've got to make a cut through the object I want to analyze, that shaft from A to B, and then analyze that, okay? So if I do that, I'm going to have this internal cross-section right there, and then I'm going to take that sketch, take the entire left side, and I'm going to pull it up here, and then I'm going to find the internal torsion by going sum of torsions is 0 and setting that equal, and summing them up, and I'll find that internal torsion that occurs between A and B, okay? So what I'm going to have then is negative 200 plus the torsion from A to B. So the torsion from A to B is 200 Newton meters. Okay. So I'm doing the same sort of thing I did with those linear problems. I'm finding the reaction at A, then I'm cutting through whatever it is I want to solve for, and I'm taking one whole side from there, the cut, back to the reaction. And I'm summing them up and setting them equal to 0. And that gets me that internal torsion, 200. Okay? Now this is the more formal way to do it, okay? Now if you want to do it more informally, you can say, well, I got 120 going positive and I got 80 going positive, so I got 200 going positive from A to B and there, right? You can also do it that way. You can look at it both ways, okay? This is, what I'm doing up above is a more systematic sort of way. Okay. We doing all right with that? It's the same idea as the linear stuff, the PL over AE that we did. We got to find those internal loads, so an internal torsion. So you want to come up with that torsion from B to C? Anywhere between B and C, what's the internal torsion that shaft is resisting? And see, the internal torsion is what's going to cause the twist. So on a typical cross section, anywhere between B and C, what's the internal torsion on that? What's that? Yeah, I think it's positive though. Yeah, because you take the left-hand side, it's equilibrium. So you got negative 200 and then positive 120, and then whatever the unknown is. If you're like, you can see set it equal to 0. If you start with a reference point, set it equal to 0, it's equilibrium. All right, so start at that reference point and work your way out. Okay. And again, there's two ways to do it. You could kind of do it in this formal way I'm describing. I've got that free body diagram set up already. So you can go ahead and put the torsions that you know are on there, 200 Newton meters. And then what's going on at B? 120? I think so. And solve that equation out, and what you're after is the internal torsion right there that we'll call TAB, or TBC, I'm sorry, TBC. Okay. Something like that. And you know, this is a systematic way to do it. Start at the reference point and work your way out. But again, as I've mentioned, there is kind of a common sense aspect to this. That's what the torsion in BC is. It's the torsion at the end. It's 80. It's positive. I mean, that's okay. We're doing all right with that? So those are the torsions inside. That's what makes things deform, is the internal loads. So once we got that, we can just plug everything in. Because what we're doing here, we're doing phi is TL over IG. We've got all this stuff now. We figured everything out. We just plug in. So for AB, we have an internal torsion of 200 Newton meters. I got the units over there on the left. The length is 0.8. I is 1.27 times 10 to the minus 6. G is 7 times 10 to the 9. So then phi is TL over IG. And that comes out to be a positive 0.01797 radians. So that's the twist in the shaft from A to B, because these parameters only hold in that section AB. Once you get beyond that, those numbers change, so you can't use it anymore. And then you just do the same thing for BC. Just plug the numbers in, run them. You know, you'll notice if you track the units, which, you know, of course, we always want to be doing that. You're going to have Newton meter squared on the top and Newton meter 4 over meter squared, which is Newton meter squared on the bottom. And that comes out to be no units, which for an angle often means radians. So that what that is a radian, which is a unitless angular measurement. Okay, so I can do the one on the right also. 80 is the internal torsion. The length is 0.5 meter, 0.50 centimeters, 0.5 meters. I've got the moment of inertia. I've got G. Plug everything in, I get 0.02274 radians. So what I have there is the twist from A to B is the 0.01797, and the twist from B to C is the 0.02274. So the total twist from where the motor is out to the end of the shaft at C is just the sum of the two, 0.04071 radians. Converting that into degrees, I got 2.33 degrees. So the end of that shaft, if I painted a dot on the top of the shaft at A, and then a dot on the top of the shaft at C, when it's not spinning and then started doing this, that dot at C is going to lag behind A 2.33 degrees when it starts spinning. Okay. So I'm just a civil engineer. I don't know much about stuff that moves. You know, I don't like my stuff moving generally. But if you're a mechanical engineer, you might care about that stuff, right? Because again, and used to be, you know, again, so many people work on their cars. No, they don't anymore. But you know, if you look at that crankshaft, that's got different pieces to it that are moving, and it's all, everything has to move together, right? The intake valve has to open at the right time. The valves have to close when the spark plug fires, right? Then when you got the exhaust, that exhaust valve has to open. That all has to be very, very precisely timed. If that isn't working right, you know, you got problems. And that's all based on the crankshaft, right? Okay. You got lifters and you got all sorts of things coming off the crankshaft. The crankshaft spins and makes all that happen. So if your crankshaft starts spinning and starts rotating those mechanical devices that are lifting the valves and opening the valves, I should say, you know, and getting top dead, getting the piston up to its maximum compression stroke and all that stuff, if that starts getting out of timing, the motor's not going to run right. So this is something you got to be thinking about. Okay, so and then I've got this last little bit here. Let's see. Okay, we got 1750 revolutions per minute. That's an RPM. Okay, very common unit that I think we're very familiar with, but it's not really what I call a native unit. It's not one that works really well. You usually have to convert out of that. An RPM is a revolution per minute. A revolution is one turn of a circle, which is 2 pi radians. So a revolution is 2 pi radians. A minute is 60 seconds. So that means that shaft is spinning at 183.3 radians per second. And so if you've got that, that twist from B to C, if B and C are both connected to parts that are supposed to mesh together as they rotate in some fashion, or they're doing things that work together, you've got to account for just a little bit of a time lag once that thing starts to spin. Okay? They're not going to be at the same position. They're going to be offset, but it's just a little bit. But you know, if you've got your motor doing 4,000 RPM, that's, you know, it's moving very, very fast. So, you know, that might be a significant difference there. So that's the time lag between when B hits top dead center and C hits top dead center. Right there. Okay. Got any questions on that?
Yes. For the directions with the right-hand rule, can you explain that?
Yeah, right-hand rule, it's just a sign convention. Of course, it's used for moments, you know, in 2D. Counterclockwise is positive, clockwise is negative. What you do, like take that 80 Newton meters on the end. If you think of that in 3 dimensions, that shaft is kind of lying flat on the paper. Your fingers would wrap behind the paper, then come out the top of the paper and curl over. That's how you would represent that moment. If you do that, your right thumb points to the right for that 80. So that's a positive.
So Okay, so right.
Yeah, to the right is positive. If your right thumb, if you curl your fingers in the direction of the torsion, the way your right thumb points indicates the sign.
Oh,
That's, I guess that's basically it. Okay. All right, couple of things to do here. How about 261, 3, and 272? So 261, 263, 272. We'll make those due on Friday. And that should be the 14th, I think. Yeah. Okay.